Hi, the next topic is local regression. So local regression is non-parametric version of regression. So it does not depend on specific finite number of parameters. It's more data-oriented method. Okay, so we want to fit the curve. We want to estimate the curve y is equal to f of x. And how to estimate the f at x naught. So the local regression is just the simple regression, the simple function such as a straight line regression, but we only use a certain proportion of observations which are close to x naught. So remember last time that we discussed the local regression ideas. So if we have the foot size data and height data for many people, and okay, so suppose we want to estimate the people's height based on the foot size. Then once you observe a foot size, probably you want to collect the observations which have similar foot size. Then we can estimate the height of the new person. So it's pretty intuitive to use observations closer to x naught. And also, the observations closer to x naught are given higher weights. So if we have 10 observations similar to x naught, then if some observations are really close to x naught, we put more emphasis on that information. And we have some emphasis on other maybe 9 observations, and we don't put any weight where if the x is far from x naught. Yeah. So what percentage of observations should be taken? So what's the optimal S? That is the one question. So if we use large S, then f hat becomes smoother in terms of x. So think about S is 100%, 1. Then we use all observations, and if we put equal weight for all observations, then f hat of x is just the y bar. So it's very smooth. So variability of y hat is small, so variance of y hat is small, but the bias is larger. So if we fit the f of x is equal to constant, of course, it has large bias at many points. So on the other hand, if we use a small s, then f hat is bumpier, the more volatile, so variance is larger, but bias is smaller. So we have trade-off between large s and small s. So S has to be optimized by cross-validation. So S is a hyperparameter, so it has to be determined somewhere, and usually by cross-validation. And one fundamental problem in local regression is that we cannot estimate fitted value at all possible x. So given x naught, we can estimate f hat, but we have to do that for all x. That is impossible. But usually we can estimate y for just limited number of observations. For example, in a training set, if we have 100 observations, then we can use those 100 observations to estimate f hat. And this is the graph we discussed before. So basically, we use only limited number of observations, maybe 20% or 30% observations. So to fit the value at x naught here, that we only use this orange data set, and we don't use these blue data points. And also we put more weights if the observations are close to this x naught in terms of the x coordinate. So we have higher weight here, but lower weight here. And this is another point. If x naught is here, we use these orange observations and we don't use these blue observations. Then fitted curve becomes this orange curve. And the blue line is the true curve which is used in the simulation. So you can flexibly fit the curve. And this is a concrete algorithm for local regression. So to estimate the f hat of x naught, at first find the 100s% of observations which are close to x naught. So say x1 to xk. Then we assign the weight, the k of xi x naught, and k of xi x naught is larger when xi is closer to 0 and smaller if xi is distant from x naught. And if xi is not 1 over x1 to xk, then we define weight as 0. So we ignore that observations. Then we estimate the coefficients of regression y is equal to beta naught plus beta 1x by minimizing this. So this is basically least square regression. So we minimize the sum of squared error, but we have weight here. So if xi is close to x0, we put more emphasis. So this is called weighted least square. And this is one application of weighted least square method. So we can estimate beta naught and beta 1 here. So we use the beta naught hat and beta 1 hat to estimate the f hat of x naught. So this is the explanation for local regression. So in the next video, I will do our implementation of local regression. See you then.